Hi, I'm Guillaume Jeanneret. I present my work text-to-image models for counterfactual explanations. The NNs have achieved major breakthroughs in computer vision, but the overparameterization makes them uninterpretable. This is an undesirable feature in safety-related applications. So, the field of explainable AI attempts to shed light on the nature of their decision-making process. There are two major branches in the XI community: interpretable by design models that propose creating architectures that show interpretable features, and post hoc explanations, search to understand already trained model. We focus on the latter, and more specifically on counterfactual explanations, which searches to answer the question, what do we need to add to X such that the model changes its prediction by adding meaningful modifications? Current solutions for vision counterfactual explanation systems use gradient-based optimization techniques, implying that they need access to network parameters and its architecture details. This is what we refer to as the white box setting. In this paper, we went a step further for privacy and model protection, and proposed time to generate counterfactual explanations in a black box setting. This is, we only need the input and its prediction. Hence, our contributions are as follows. We propose time, which leverages Stable Diffusion to generate counterfactual explanations. Our proposed approach is completely black box, and our counterfactual explanation method is based on the distillation approach and does not require any optimization during the inference, unlike most methods. Our method consists of two steps: a distillation phase, where we transfer the knowledge of the classifier to Stable Diffusion, and a generation phase, where we leverage novel inversion techniques to noise and guide the diffusion process to the target class. Before explaining our method, we identify two biases learned by a classifier. The context bias, which relates to the image generation process, for example, taking street images from a car for autonomous driving. And the class-specific bias, where we have specific features used for the classification. For example, stop when the model detects a red light. So, in order to distill this information, we took a textual inversion standpoint. In a nutshell, textual inversion teaches Stable Diffusion to generate a certain object or style by training a new textual embedding by minimizing the DDPM loss on a set of images. Hence, to learn the context bias, we begin by taking all the images in the training dataset. Then, we learn a new text embedding using the textual inversion algorithm, thus giving Stable Diffusion information about the word learned by the classifier. We take a similar approach to learn the class-related token. Firstly, we filter the dataset and select only those images classified as a certain class. And then, again, conduct textual inversions to learn the new embedding for this specific class. Note that we only needed the prediction and the input of the model, something that previous methods do not have. Finally, to generate our counterfactual explanation, given an example from which we want to compute its explanation, we produce its prediction and a phrase containing the context and class predicted tokens. Then we invert the image to an intermediate point and denoise it by flipping the class predicted token to the class target token, hence generating our counterfactual explanation. To further enhance the effectiveness of our method, we added a negative drift term to steer the generation more easily. Please check our paper for more details. We tested our approach on two datasets, Celeba HQ and BDD100K. Here we are going to focus on the qualitative assessment. For the quantitative evaluation, we perform competitively, yet please refer to our paper for more details. First, we compare our method qualitatively against the previous state-of-the-art DIME and ACE. In a bird's view eyes, DIME is able to produce more visually notable changes in the images, while the literature focuses on really tiny changes. From the user perspective, this could be hard to spot on. Additionally, our modifications are visually more appealing than previous approaches. BDD is more challenging, since stopping or accelerate depend on multiple factors. Our counterfactual explanation produces many variations or many additions for this task, which is not ideal. Yet we can learn what the model uses for this from these examples. For instance, if the model detects an object in front of it, it will stop. And finally, time is an efficient method for training and inference. Training-wise, all state-of-the-art methods require training from scratch or fine-tune a generative architecture, which is very costly. In contrast, we train a simple textual token. Inference-wise, it does not require any of the optimization, thus reducing the computational burden. For example, time takes about 100 teraflops to compute a single counterfactual, while 8 takes about 279 teraflops. Thank you for your attention. Please check our code and webpage for more information.